Okay, geometry students, this is the second installment of the massive Chapter 4 that we're trying to review for. And Chapter 4 got into a lot of specifics on triangles. This was kind of the first unit where we really started to see that triangles are a very special shape in Euclid's geometry. There's a lot of relationships, a lot of things to know and to look out for when working with triangles. And we really kind of started getting into that for the first time. Okay, so looking at triangle congruence. Okay. Anyway, what we're looking at here is, the whole topic of congruent polygons is, of course, being able to prove that every single set of corresponding sides are congruent from one polygon to another, and every single set of corresponding angles are congruent from one polygon to another. But the thing that we discovered with triangles is that it's not necessary to be able to prove every single set of corresponding sides congruent or every single set of corresponding angles congruent. If we could just prove a certain set or sets of sides congruent or a certain set or sets of angles congruent, then that would be enough for us to determine that two triangles are congruent or not. So for the first couple of days on this particular part of the unit, we were looking at the shortcuts that were available to us to decide if two triangles were congruent or not, even if we didn't have all of the information that we'd like to have to go through the main definition for polygon congruence. Anyway, the first shortcut we looked at, and most of these are considered to be postulates, and remember a postulate is a kind of a common sense rule that absolutely must work the way that it is said. And then we also have some theorems, and remember that a theorem is not a common sense rule. It's something that actually requires a big drawn out explanation in order to understand that that is the way that the thing works. Anyway, the first one we looked at was called the side-side-side congruence postulate. And this one basically says that if you have all three sets of corresponding sides congruent from one figure to another, that you don't actually have to prove anything about the angles in the triangles, that having the three sets of sides would be enough, and you could establish that two triangles are congruent by side, side, side. Now, of course, remember, anytime you use one of the shortcut postulates or theorems, you are going to be required to identify which particular one that you use. So this is not a, is it congruent, yes or no, let me toss a coin and see what I think. Okay, if you're going to say that they are congruent, you will have to say that they are congruent by, in this case, side, side, side. And if you can't pick the correct shortcut, then that is just the same as missing the entire question. The second one that we looked at was the side angle side congruence postulate. And if you remember back to these, you'll remember that these are listed in order. Okay, so it's not like, hey, we just need a set of sides and a set of angles and a set of sides anywhere in the triangle. You actually need them in that order. So you can see that we need two sets of sides and then an angle between those two sets of sides. Okay, so wherever those two sets of sides are in our triangle, they're going to join together at a vertex. At that vertex, that is an angle. We need that angle to be the one that actually works out with us. Okay, so anyway, side angle side says if two sides of one triangle are congruent to two sides of a second triangle, and the included angle, which means the angles in between those two sets of sides, are also congruent, then the triangles are going to be congruent. So you don't actually have to worry about the third set of sides, and you do not need the other two sets of angles. You can identify that the triangles are congruent, and you would have to identify that they are congruent by the side angle side congruence postulate. Okay, we looked at some examples. We had a couple of more of these guys, and we kind of split them into 2 days, so it wasn't too much information overload. And these deal more with the angle measurements than they do the side measurements. Okay, so very similar to side angle side, we have angle side angle, and of course the labeling of that is specific. So we're looking at two sets of angles in the triangles, and then the side that connects those two sets of angles, so the side in between them. Okay, so it says if two angles of one triangle are congruent to two angles of a second triangle, and the included sides, meaning the sides that are in between those two sets of angles, are also congruent, then your triangles are congruent. So in this case, you do not need to know about the third set of angles, and you do not need to know anything about the other two sets of sides. You could say your triangles are congruent by angle, side, angle. And again, you have to be able to identify that that is the postulate that is being used, angle, side, angle. The last of the congruent postulates was angle, angle, side. And again, very similar information being used, two sets of angles and one set of sides, but notice the positioning of the side in the labeling of this congruence postulate. Okay, you have two sets of angles and then a set of sides. That means that the one set of sides that you can prove to be congruent is not going to be positioned in between the two angles that you do know that are congruent. Okay, so we're looking at if two angles of one triangle are congruent to two angles of a second triangle, and a non-included side, meaning it's not between the two angles, is congruent to its corresponding side, then your triangles are going to be congruent. And again, if you can prove this, then you do not need to know the third set of angles nor the other two set of sides. And of course, as always, if you're going to imply that this congruence postulate is the reason why your triangles are congruent, you're probably going to have to identify that angle, angle, side is the shortcut that allowed that to happen. Okay, now we did take a look at one other misconception, and there's a lot of reasons that float around in sophomores' minds as to why we would not allow you to use something like angle, side, side, and typically teenagers theorize that we wouldn't let you use angle, side, side because of what it spells out when you come time to identify it. Okay, so it's not that ASS spells a bad word, and that's why we don't want you to use angle, side, side. We don't want you to use it because it simply does not work. Okay, the other four rules, the real rules that we have, side, 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 angle, side, angle, and angle, angle, side, we use those rules because they work. When we see them and implement them, it guarantees that the two triangles that we're looking at are congruent, that there is no possibility that the two triangles could not be congruent. The problem with angle, side, side is that even if you can find it in a problem, it still does not guarantee that your two triangles are congruent. In fact, there are two distinctly different triangles that can exist even with the presence of angle, side, side trying to apply. So if you see angle, side, side, do not fall into the trap. It does not guarantee. Okay, some people kind of seem to think that if they can find any combination of sides and any combination of angles, that means that you can prove that your triangles are congruent. That is incorrect. There are only four, and we've already covered them. Okay, so any other combination of A's and S's will not work other than side, 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 angle, side, angle, and angle, angle, side. Okay, after that we got away from the triangles just a little bit and started looking at polygons in general. Okay, now as you knew in geometry or in junior high, okay, similar polygons meant same shape, different size, and that's absolutely true. It's a good verbal description, but you better understand what happens mathematically in order to have the same shape but different size. Okay, in order to have the same shape, your corresponding angles are going to have to be congruent to each other. If you allow the angle measurements to start opening up and closing, well, that's kind of the difference between a parallelogram and a rectangle, stuff like that. Okay, so the angle measurements, corresponding angle measurements, have to be congruent to cause the same shape. In order to allow for the possibility of the size change with similar polygons, we don't need our corresponding side lengths to be congruent. We do need them to be proportional. Okay, so the key to being able to establish the side lengths is we have to know, first off, what corresponds to what, okay, and then we have to know, of course, how to set up a proportion and how to solve it. Now, we've already talked about figuring out what corresponds to what. Okay, so remember, we are not talking about things existing in the same place in two different figures. Okay, so do not think top corresponds to top and left corresponds to left. That's very weak-minded thinking, and it's absolutely not correct. You need to be looking for similar properties from one figure to another. For example, where is the largest side of one figure? That will correspond to the largest side of another figure, wherever it happens to be. Or the smallest angle will correspond to the smallest angle in another figure. Or maybe you have some tick marks or some angle congruency marks that you can reference from one figure to another. That is why things correspond from one figure to another, not because they are sitting in the same place. Okay, so on to the solving. A proportion is just a fancy way of demonstrating a relationship between two ratios. Now, a ratio is just a fancy word for a fraction, two numbers that are being related to each other. And in the case of similar polygons, the relationship is the corresponding part from one figure to another. Okay, so we're going to set up two ratios, okay, that are going to connect our figures from one polygon to the other. Okay, and we will set those ratios equal to each other. Two ratios equal to each other is a proportion. Now, as you can see there at the middle and the bottom part of the screen, there's two different ways proportions can be expressed. One is in the what they call standard format, or fractional format of the proportion. That's where you have one fraction equals another fraction, and it's read A is to B as C is to D. Another identical way of writing it down, okay, or expressing it, is what they call the ratio format, and that's where they use colons instead of fraction bars, but it does not change the proportion or how it reads. A is to B as C is to D. Okay. Typically, we like the fractional format a little bit better because we are getting ready to cross multiply. So if you happen to run into a proportion that is in ratio format, you might consider rewriting it into the fractional format so that you can cross multiply over your equal sign. Now, proportions can be used for a couple of different applications. We can decide if two ratios are in fact equal by cross multiplying and seeing if you end up with the same result on each side of the equal sign. If you do not, then your proportion was a bad one, and those ratios are no good. If it turns out the same, then the proportion was a good one, and the ratios were the same. Okay. Second thing we can do, and this is what we use them for in similar polygons more than anything else, is we use them to find a missing piece of information. So when we set up our proportion, if we only have one unknown in our problem, then we can solve for that unknown by cross multiplying. You end up with a variable in your problem, and then you have your 5 steps to solving an equation. Your parents' complaints vary for everyone. Okay, solve your variable, and then you can always check it like any other Algebra 1 problem by plugging your value back in to the problem in place of the variable and seeing if you end up with a true statement. Okay, so again, trying to figure out what corresponds to what, that's the challenge for many people, and you need to set up your proportion. And it's not just one proportion. Okay, in the case of a triangle, since you have 3 different side lengths, it actually takes 3 different proportions to see if the figures are proportional. Okay, so I offered a system to you, and what I typically said with what I do is I start off with the left-hand figure or the top one, depending on how the diagram is oriented. Okay, I start off with the left one, and I usually start off with the smallest value. So in this particular case, I took the smallest side length from the red triangle on the left, and I related it to the smallest side length from the blue triangle on the right. So that was 4 to 6. Okay, and then I moved on to the middle-sized side lengths, which were the 6 and the 9 from left to right. Cross multiply to see if it was true, and it was. Now that does not mean that the figures are similar because there are still 2 other proportions to set up. Okay, now I've already set up ratios from the smallest side lengths to the middle side lengths. Okay, so I'm going to take that same middle ratio again, 6 to 9, and I'm going to relate it to the largest side lengths from left to right, which is 11 to 16.5. Cross multiply there, see if it's true, and it was. Okay, one more proportion to look at, and that was the large set of sides being compared to the small set of sides. So I already knew those two ratios. I just set them up in a proportion together, 11 to 16.5 and 4 to 6. Cross multiply and see if it's true, and it was. Since all of the sets of corresponding sides were in fact proportional, then I would be able to say, yes, these two triangles are congruent by side, side, side. Because again, I didn't know anything about the angles, but I did prove that all three sets of corresponding sides were proportional. Okay, so again, it doesn't mean or the corresponding does not depend on how the figure is sitting. It has to do with what properties the figures share from one figure to the other. We came across a new symbol for similarity. It is a little squiggle, kind of similar to the guy that's been sitting on top of our congruent symbol all this time, but he does not get the equal sign because they are not equal. They are just similar. Okay, so we worked through some examples. You can look back at that lesson if you need extra help. Okay, continuing on with the discussion of similarity. Okay, you can't hardly talk about similarity without talking about scale factor. Now, scale factor is basically a ratio that determines how two similar figures are actually related to each other. Okay. Now, one of the things that we looked about, kind of introducing the idea of scale factor, is of course we had three different ratios for our triangles on the example we just looked at. And if you're looking at a quadrilateral, you'd have four different ratios, and a pentagon would have five different ratios, and so on. Okay, but there would be ratios relating one figure to the other figure as far as corresponding side information. And there was actually more information going on in those ratios than we looked at to begin with. And in the cases of all the ratios, what we did is we took them all and we reduced them down to simplest and most proper terms. Okay, so in this case, that meant reducing a couple of the fractions, and in some cases, the right-hand case, they're eliminating the decimal point. We do not typically end up with decimal points in fractions. That's what we call a compound fraction, and it should be simplified out of there. But in short, what you can see right there is that each of the three ratios, whether it was the small set of side lengths or the medium set of side lengths or the large set of side lengths, we ended up with the exact same ratio each and every time. And that is not an accident. That is what will happen with any two similar polygons, no matter how many types of how many sets of sides they have. Okay, and this ratio that all of these guys reduce down to is what is called the scale factor. Okay, now the scale factor is kind of what tells the polygons, okay, if you're going to get from smaller to larger, if it's a small number becoming a bigger number, or larger to smaller. Okay, big number becoming a little number, and so it tells us whether we are enlarging or reducing, and then by the numerical values in that ratio tells it by how much it's reducing or enlarging by. Okay, so anyway, we looked at some examples of scale factor. Hopefully you kind of remember how all that works. And one of the things that we discovered, a handy tool about scale factor, is it can be used to help us solve for missing information in our similar polygons. In other words, we can install scale factor into our proportions as one of the ratios to go along with our similar polygons. That's very helpful. Okay. Then this focus of the conversation came back to triangles, as it always seems to do. Okay, so with similar triangles, just like with the discussion on congruent triangles, similar triangles, if you can just find the right information in the right orders, then you can predict whether triangles are going to be similar or not, even without having all the information that you'd like to have. Okay, so there were three such similarity rules here. Okay, and one of them for the triangles was the angle-angle similarity postulate. Okay, and for similarity, since our side lengths are allowed to change, there's not so many restrictions. Okay, so you can predict that two triangles are going to be similar just by knowing that both of the or two of the angles in our triangles are congruent. If you can find two sets of corresponding angles congruent, then you can say that your triangles are similar by angle. Okay, and yes, you do still have to identify which particular shortcut you are using. If a question does show up, that's what it's going to focus on, not yes or no, whether they're similar or not, but they'll say, hey, the following two triangles are similar, which postulate can prove it? And then you'll have four answer choices to select from. Okay, the second one that we looked at was side, side, side. We did have this one for the congruence, triangle congruence as well, but of course we're looking at different information about the side lengths this time. We're no longer interested in the side lengths being congruent as it was with triangle congruence, but we do need those side lengths to be similar. So unfortunately, there's still a lot of work to be done to determine that you have similarity, because with three sets of side lengths in your triangle, that means three sets of proportions. Okay, to set up your ratios. And if all of the ratios work out, then you can say that all of your triangles are similar by side, side, side. Okay, it still did take the same amount of work, so what's the benefit of this? The benefit of this is we don't know any of the angle information for a problem like this one. Okay, so that takes the angle information out of the problem. We just have to do the legwork on the sides and make sure all of our proportions are good. Another one that we did have for the congruence was side, angle, side. We still have that one for similarity. Okay, so the same basic idea does apply. The only difference is, of course, the two sets of sides that you have going on in side, angle, side, they need to be proportional to each other. Okay, so have a look at that proportion. If you have a good set of sides, proportional with each other, and the angle that is between those sets of sides congruent, then you've got side, angle, side. Okay, the rest of it was just examples. Anyway, that pretty much wraps up the second part of Unit 4. That's a ton of information, and we're still not done yet. Okay, but that concludes your Part 2, Unit 4 review.